Machines do many things. They help move dirt, lift things, and pump oil from the ground. Machines help skiers to get to the top of a mountain. And travelers to fly. There are also many machines that we may not think of as being machines. These are machines that we may use every day. They may seem too ordinary, too simple to be machines. But by understanding simple machines, you can understand much more about even the most complicated machines. We don't usually think of a playground as a place where work goes on. A playground is a place to have fun. But despite appearances, while these children are playing, many of them are also doing work. This kind of work is different than schoolwork, which involves thinking. In science, the definition of work is moving something over a distance. So this boy is doing work by moving his brother across the playground. Work like this requires force. The definition of force is any push or pull. Pulling a wagon involves force. Here's still another definition. Whatever is being pushed or pulled is called the resistance or load. Here, the boy being pulled in the wagon is the load. And here, the little girl being pushed on the swing by her mother is the load. Not only is there a lot of work going on, but this playground is also full of machines that help people do work. Machines on a playground? Well, in science, a machine is anything that helps people do work. Machines often help by reducing the force it takes to move something over a distance. So this seesaw is a machine because it helps these two boys lift each other up in the air. And this wagon is a machine because it reduces the amount of force it takes to move a younger brother across the playground. Machines like the seesaw and wagon may seem pretty far removed from complex machines like the ones shown here helping repair a road. But all machines are alike in that they help people do work. All machines are alike in another way, too. No matter how complicated some machines may look, all machines are made up of combinations of simple machines. Simple machines are machines that have few, if any, moving parts. There are 6 types of simple machines. These are the lever, the wheel and axle, the pulley, the inclined plane, the screw, and the wedge. Let's look first at the lever. Remember that the definition of a simple machine is one that has few, if any, moving parts. All levers are made up of the same few parts. First, there is a beam or a rod, also known as a lever stick. The lever stick rests on a point called a fulcrum. The lever stick can rock back and forth on the fulcrum. Levers help us lift things. The weight that a lever lifts is the load or resistance. And the push or pull that moves the lever is the force. And that's all there is to this simple machine. You can see levers in many places. Can you think of any levers? Well, you've already seen one in this program. A seesaw is a lever. Can you tell where the fulcrum is? It's where the seesaw rocks back and forth. As the children lift each other up, they take turns providing the force and being the load. Suppose you had to lift a very heavy rock. To help, you could use a board and a log as a lever. Put the log, which acts as the fulcrum, under the middle area of the board, and then push on the board to lift the rock. First, try pushing on the board close to the fulcrum. You might need help from a friend. Then try pushing on the board farther away from the fulcrum. You would find that it takes much less force to lift the rock. In fact, you might be able to do it by yourself. So what does this teach us about the relationship between force and distance in levers? Well, one thing it tells us is that the farther away the force is from the fulcrum, the less force it takes to lift a load. In fact, if we double the distance of the force from the fulcrum, it takes only 1/2 the force to lift the load. The levers that we've looked at so far have all been of one type. They've had the load on one side, the fulcrum in the middle, and the force on the other side. Such levers are called first-class levers. But there are other kinds of levers. In some levers, the fulcrum is not in the middle, but on one side. The load is in the middle, and the force is on the other side. Such levers are called second-class levers. A wheelbarrow is an example of a second-class lever. The fulcrum of the wheelbarrow is where the wheel is. The load is what is in the wheelbarrow, and you provide the force by lifting the handles. Here's another example of a second-class lever. A nutcracker. The fulcrum is at the end of the nutcracker. The load, the nut, is in the middle, and you provide the force by squeezing the handles. There is also another type of lever. With this type of lever, the fulcrum is on one side, the force is in the middle, and the load is on the other side. This type of lever is called a third-class lever. Raking leaves is an example of a third-class lever in operation. The fulcrum is the hand at the end of the rake, the other hand provides the force, and the leaves are the load. Now let's look at another kind of simple machine. People depend on this simple machine all the time. Without this simple machine, there would be no cars or bicycles. You couldn't roller skate or skateboard. What is this simple machine? This simple machine is a wheel that is attached to a post called an axle. The wheel and axle turn together. We are all familiar with wheels and axles on cars and toys and roller skates. Do not recognize right away. For example, a doorknob is a wheel. If you took the doorknob off, you'd see that it is attached to an axle. A wheel and axle actually is a kind of lever. How can this be? Well, it may seem clearer if you think of the bar of a lever as a spoke in a wheel, and the fulcrum as the axle. Add some more spokes all the way around, and a rim, and you have a wheel. Remember how, with a lever, when you increase the distance of the force from the fulcrum, less force is required to lift the load? Something similar happens with a wheel and axle. Here's an experiment you can do that will demonstrate what we mean. With one hand, hold a stick at the middle. Imagine your arm as an axle, and the stick is the spoke of a wheel. Now have a friend grab the stick with both hands as close to your hand as possible. Have her try to turn the stick while you try to keep it still. Think of this as trying to turn a small wheel. Now have your friend make the wheel bigger by grabbing the stick farther away. Notice how much easier it is to turn the stick. So what does this tell us? It means the greater the distance from the axle, the easier it is to turn a wheel. In other words, it takes less force to turn a large wheel on an axle than a small one. Another kind of simple machine is related to the wheel. This simple machine is called a pulley. A pulley is made with a wheel that has a groove in it to hold a rope. By pulling on the rope, you can lift a weight or load. There are different kinds of pulleys. One kind can be found on top of a flagpole. It is called a fixed pulley because it remains anchored to one spot. A fixed pulley doesn't decrease the amount of force you need to move something, but it does change the direction of a force. You pull down on the rope, and the flag goes up. The pulley doesn't make the flag seem any lighter, but without the pulley, you'd have to climb to the top of the flagpole. A clothesline provides another example of a fixed pulley. Pulling the rope one way will move the clothes in the opposite direction. Even though a fixed pulley doesn't reduce the amount of force necessary to move something, it still fits the definition of a machine because it helps us do work. In this case, it helps us do work by changing the direction of a force. Here's an experiment you can do with a fixed pulley. Attach one end of a rope to a weight, such as some books, and the other end to a spring scale, which measures force. Then measure the amount of force needed to lift the weight using a fixed pulley. Here we've frozen or stopped the video picture of the scale as the weight is being lifted. The scale shows it takes about 38 newtons of force to lift the books. Newtons are a unit of measurement that are used to measure force. What if we were to use a different kind of pulley? A movable pulley. A movable pulley moves along a rope. One end of the rope is fastened to a fixed point, such as a hook, while you pull on the other end. Using a movable pulley, try lifting the same weight that you lifted with a fixed pulley. Using the spring scale, we see here that it takes 19 newtons of force. With a fixed pulley, it took 38 newtons. So a movable pulley cuts the amount of force needed to lift something in half. Because movable pulleys decrease the amount of force necessary to lift something, they often are used with fixed pulleys, like this. This type of setup is called a block and tackle. Movable pulleys are commonly used along with fixed pulleys to lift heavy loads, like this bucket of cement. This movable pulley is being used by a crane. To see another kind of simple machine, let's return to the playground. This slide is a type of simple machine called an inclined plane. An inclined plane is a slanting surface. This slanting surface makes it easier to move things to a higher place. As with other simple machines, an inclined, for example, it takes a lot of force to lift this box up to the back of this truck. Is there a better way? Using a ramp gives you an inclined plane. It allows you to use less force to move the box into the truck than by simply lifting it. Here are two inclined planes. They both have the same height, but one is much longer than the other. If you pushed a weight up both planes, which inclined plane would require less force? Well, let's look at the short inclined plane first. Let's say the sloping surface of the inclined plane is 10 meters long. Let's say also that it takes 100 newtons of force to push the weight up this 10-meter inclined plane. Now let's look at the other inclined plane. This time, suppose the sloping surface of the inclined plane is twice as long, 20 meters. To To push a load up this plane would take only half as much force, 50 newtons. The longer the distance, the less force it takes to move something up. Here's a problem for you. Suppose you had to bicycle to the top of a mountain. Obviously, going straight up the mountain would be impractical. No bike could go straight up the side of a mountain. So what could you do? Well, you could build an inclined plane, but it would have to be very long, and it would have to start a long way from the base of the mountain. This might be a very expensive and impractical solution. But there is another way. There is no reason why an inclined plane has to be straight. What if you wrapped an inclined plane around the mountain? This is, in fact, how most mountain roads are built. They wind around the mountain rather than going straight up the mountain side. Does the way the inclined plane winds around the mountain remind you of anything? Look at this common screw. A screw, in fact, is really an inclined plane wrapped around a post. The screw is another type of simple machine. Some screws, like wood screws, have sharp points. The winding edges are called threads. When you twist the screw into a piece of wood, the threads grip the wood very tightly. Because of the winding threads, you have to turn the screw a greater distance than if you were to push it straight into the wood. But turning it this way takes less force. Screws are useful in many ways. They can be used to move or lift things. This man is using a jack to lift his car. If you look closely, you can see that the jack includes a kind of screw that makes it possible to lift the car with less force. Like the screw, the wedge is another variation of the inclined plane. In fact, you could think of a wedge as being two inclined planes put back to back. Wedges are used to push things apart. When you push on the wide part of the wedge, the force will push the narrow edge into something, pushing it apart. Wedges have many uses. They can help split a log. Whenever you cut something, you're using a wedge. Knives are wedges with thin, sharp edges. The tip of a nail is a wedge. The wedge shape makes it easier to drive the nail into a piece of wood. We even have wedges inside our mouths. Your teeth are wedges that make it possible to chew an apple. Levers, wheels and axles, pulleys, inclined planes, screws, and wedges. These are the 6 types of simple machines. You see these simple machines all around you, but sometimes you might not recognize them right away. Look at the sharp, pointed bows of the canoes. They help the canoes cut through the water. Can you tell what kind of simple machine a canoe's bow is? The wedge shape makes it easier for the canoes to cut through the water. Here's another boat. It is an example not only of a wedge, but also of another kind of simple machine. Look at the oars. Do you know what kind of simple machine the oars are? The oars are levers. What kind of simple machine helps raise this shade? Do you see how a pulley is used to raise the shade? What about these scissors? Are there simple machines in these scissors that make it easier to cut paper? If you answered wedges, you would be right. Each blade of the scissors is a wedge. But you might also have answered levers. The scissors are 2 levers joined in a single fulcrum. Many of the things we see around us are made up of several types of simple machines. Take a look at this drill. One part of the drill is in the form of a screw. But the drill also has gears that are a type of wheel. Machines that consist of 2 or more simple machines are called compound machines. This bulldozer has parts that include wedges, levers, wheels, and screws. Compound machines can have many parts that work together in ways that may not be immediately clear. But no matter how complicated different machines may appear, every machine is made up of combinations of the 6 simple machines that we have looked at in this program. In this program, we've seen that work means moving something over a distance, and that in order to do work, you need force, any push or pull. We've seen that machines help people do work, and that simple machines are parts. Simple machines help people do work by reducing the amount of force needed to move or lift something. Or simple machines may help us do work by changing the direction of a force. And finally, we've seen that all machines, no matter how complex, are made up of simple machines.